First thing we'll look at is the domain of this function. And so the definition of domain has to do with the set of all input values. Now most students will say that domain is the x values, but notice that if I have an x value of -6, for example, I have no y values to go with that. So really -6 is not part of the domain of this function. I have to be sure that the input values I'm including in the domain are ones that produce defined output values. Okay, so let's see if we can figure out this function's domain. I'm going to start off by writing this in set notation, so I'm going to say D for domain, open up a set with a curly bracket, and then I'm going to use this cursor, and I'm going to notice that if I go from the far left, -infinity, all the way up to -6 and even beyond, as I said before, there's no y values here. I'm going to continue scrolling over until I get to -5. So now you see that I have a y value at x equals -5. That y value is 4. And so I'm going to record -5 as the beginning of my domain, and I'm going to use a square bracket because it includes that point, x equals -5. I do have an output there. I'll continue scrolling now to the right. I have outputs at all of these x values all the way up to 0. When x equals 0, I'm at the end of my first part of the graph, and you see that open circle there. So at x equals 0, I'm going to put a round bracket to say that everything up to 0 is included, but not 0 itself. Now notice between x equals 0 and x equals 1 that there are no outputs until I get to x equals 1. So I've completed that first branch on the left, and I'm going to start recording the interval containing the right-hand branch. So I'm going to use the set union notation, and I'm going to open up my second interval starting at 1, and I will include that point because my x equals 1 has an output of 4. I'm going to continue to scan across here, and I get to x equals 5, and I see that I'm at the end of the right-hand branch. My y value is -2, but it's not included. So at x equals 5, I'm going to put a round bracket. And so when I put all of this together, close my set, I should have a domain that looks like what you see at the bottom of the screen. Another way to think about finding domain from a graph is what I call graph squishing. Basically what you want to do is squish the graph down from above the x-axis and squish it up from below the x-axis. So all the points, all of the lines, curves, everything gets flattened onto the x-axis, including the open circles. So as you do that, what you're going to do is, once everything is on the x-axis, you've basically identified the intervals where that graph has defined y outputs, because all your y values are now squished onto the y-axis. And so we can see that this should match the domain set that we had from the previous slide. Next we're going to talk about range. And so range has to do with the output values, or the y values. And again, most students will know this part, but what we have to be careful about is it's not just any y value. I can't say that y equals -3 is in my range here, because it isn't. So I have to worry about what are all the output values that are actually produced by the x values in my domain. So this function's range, we're going to do something similar as what we did with the domain by moving this cursor upward, okay, from negative to positive. So I'm going to open a set called R with a curly bracket, and I'm going to continue up, and notice that my graph starts at y equals -2. Because of that open circle, I'm not including -2, so I put a round bracket. I continue scanning, and I have y values everywhere. Now I want to pause right here at y equals 3. Don't get confused or fooled by that open circle on the y-axis. It certainly means that there's no y value there at x equals 0, but notice here on the left and the right where the heavy dots are, I do have y equals 3 as outputs for their corresponding x values. And so y equals 3 is part of my range. I'm going to continue on upward, and it looks like y equals 4 is going to be the end of my range. And because I do have points at y equals 4, I'm going to use the square bracket. I'm going to close my set and write my range as you see on the screen. We can do the same thing as we did with domain by squishing the graph, this time onto the y-axis. The difference here is that because I can have multiple y values, you'll notice that the two green dots represent those points at y equals 3 that I said really take care of filling in, if you will, the open circle on the y-axis. And so as the graph gets squished onto the y-axis, you're going to see that those holes get, and therefore you'll see that the range extends from -2 to +4. Now notice down at -2 there was no other y values at -2. In fact, no y values at all that were able to fill in that hole, so that remains an open circle. So let's define the word interval. We've been using that on and off, and we need to get a definition for it. All it really refers to is a range of x values or y values. Usually it refers to x unless we specify that it's y values. So I like to think of an interval as a piece of the x-axis. Now a function is increasing when y values increase as x increases. In other words, the graph is going to go up as I read it left to right. When x increases, I'm reading left to right. By the same token, a function is decreasing when the y values decrease, but again, as x goes from left to right, as x increases. And a function is constant when the y values do not change. So let's take a look at the graph and see if we can identify some of those places. Before we do that, let's also talk about positive and negative y values. We know that values of f of x, or values of y, are positive or greater than 0 when they are above the x-axis. So what you see highlighted here are all the y values above the x-axis. If we write the intervals where those things live, we can see that that goes from -5, including -5, out to -3. Now I'm not including -3 because the y value there is 0, which is not greater than 0. In other words, 0 is not a positive number. I have a second branch which goes from -3, again not including, out to 0, and not including x equals 0 because of that open circle. And then I have an interval starting at x equals 1 and extending out to x equals 4. I do not include x equals 4 because, again, the value of the function right there is 0. I can do the same thing with negative values. These are values of y below the x-axis. And so that would be where it's highlighted right there. One interval on my graph here from 4 to 5. Again, I'm not including 4 because that value is equal to 0, and I'm not including 5 because of the open circle. How about where f of x equals 0? Again, those would be points right on the x-axis, y equals 0, at -3 and +4. And so we can capture our answer that way. We can use set notation and throw -3 and 4 into that set. And there's a number of different ways that we could write that. So what about increasing and decreasing intervals? Well, f of x is increasing when the graph goes up as we move left to right. So it looks like this is the only place where that's happening. And so we'll capture the interval from -3 to 0, not including either point. Now I'm going to make a comment here about notation for increasing and decreasing and some other things. On one hand, we can say that the graph is neither increasing nor decreasing at x equals -3, and that's why I don't include it. Depending on how you want to define increasing, you might see that point included. I think for simplicity, it's easiest just to use open intervals, in other words, using the round brackets only for intervals of increase, decrease, and so on. The function is decreasing when the graph goes down as we move left to right. And so the highlighted areas would be decreasing intervals, and we would write those intervals -5 to -3, again not including either point, and then also from 2 to 5. And then finally, where is f of x constant? Well, it's constant where the values of y don't change, and they don't change if they stay at the same y value, and that forms a horizontal line or horizontal segment, and that occurs between 1 and 2. Now you notice I use square brackets there because I know that at x equals 1 my value is 4, at x equals 2 my value is 4, and so I can include those points. Now we'll talk about minimum and maximum points, otherwise known as extrema. We can talk about absolute or global extrema, meaning the biggest or smallest points in the entire domain of the function. So an absolute or global minimum would be the smallest y value on the function's domain, or possibly in a specified interval if we wanted to look at just a small piece of the graph. Now notice I've got smallest, lowest, most negative, least positive in my definition here. Those all mean the same thing, and so you may use some of those different terms or hear some of those different terms. They all mean the same thing. In the same way, absolute or global maximum refers to the largest y value on the function's domain or in a specified interval. Now a relative or local minimum is the smallest y value in a neighborhood. And a neighborhood is just a small area around a point that we're interested in. You'll see that in just a moment here. A relative or local maximum is the largest y value in a neighborhood. So what is the absolute maximum value on this graph, on this function? It's y equals 4. I have those three heavy points there, but also notice that I have an infinite number of points at y equals 4 between x equals 1 and x equals 2. That whole constant section right there is all y equals 4. Now I have a relative minimum at -3, 0. The coordinates are -3, 0. You see that dashed circle? That's an example of a neighborhood. If I consider just that part of the graph, that is my lowest point, and so that's how I can define a relative minimum. I can make that neighborhood as big or small as I want to capture the information that I want. And finally, what is our absolute minimum? Well, we don't have one here because this open circle at 5, -2 means we cannot name the lowest value. We know that -2 for y does not exist on this graph. We could say, well, maybe the lowest is -1.9, but what about -1.99? What about -1.999, and so on. So as many 9s as you want to give me, I can give you one more and get even lower, but we'll never be able to actually name the number that gives us that lowest value. So we say there's no absolute minimum on this graph. The last attribute that we'll look at is called concavity. And concavity just refers to the curvature of the graph. And curvature of a graph results from a change in slope. If you imagine a straight line that has a constant slope, if you start changing the slope as you move along that line, you're going to create a curve or a bend in the line. So when we talk about concave up, we're talking about a portion of the curve that is curving upward. In other words, its slope is increasing. The red arrow on the left has a large negative slope at the beginning, which becomes a smaller negative slope, so that's actually increasing from more negative to less negative. On the right, we have a small positive slope becoming more positive as we continue along that curve. In the same way, concave down is curving downward. The slope is decreasing. Notice that I can have an increasing function or a decreasing function with either concavity. They don't necessarily go together one with the other. So f of x is concave up, curved up on these intervals that are highlighted, which is -5 to -3 and also 3 to 4. Again, I'm using open intervals to describe these. F of x is concave down or curved down on this interval between 4 and 5. And finally, f of x is not concave, meaning that it's just a straight line, on these intervals that you see in green, -3 to 0 and 1 through 3. So again, I can use square brackets or round brackets when I'm talking about the straight segments, but in this case I really don't have to. I could use either.